Hello again. Somebody sent in a problem that they said they thought would make a good candidate for one of these kind of explanatory videos, and I looked at it and I couldn't agree more. So I thought we'd look at it. This is one of those problems, kind of like the problem you had on your last sample where the box was cut out so it folded up to make the sides. Similar to your fence kind of problems, those kind of, thinking through geometry setup kind of problems. You certainly should expect to have problems like that. And people often feel that the one that was on the test is never exactly like the one that's on the sample. Well, it's not. It's not going to be. But it's going to be based on the same kind of principles, the same principles of being able to set up a problem like this. This one is probably a little bit meatier than what you'd see in a really typical test question. But it's certainly the type of question and the type of setup that you might see. So you're asked here to find the possible dimensions for a closed box, and you're told that the volume is 216 cubic inches. You're told the surface area is 252 square inches, and you're told that the length is equal to twice the width. So we have to take those three pieces of information and figure out how big this box might be. So one of the things that I can't stress enough, and I think I mentioned this during the first sample that I wrote out, is you really want to, whenever you can come up with an excuse to draw some diagrams, draw yourself some diagrams. It really does get that visual cortex, that big chunk of meat, mostly fat, at the back of your skull working. And has it help you think through problems. So anytime you can justify drawing any kind of picture or diagram, do it. It's going to help. It doesn't have to be all pretty and in perspective like mine, but hey, it helps. Nice little art minor. Go get yourself an art minor. Makes your day that much richer. Okay, so you got a box. Doesn't have to be a great box. This isn't all that great of a box. We're told its volume is 216. You find volume by taking the height times the width times the length. You're told that the surface area is 252. Well, how do you find the surface area of a box? Well, you'd have to look at all the different sides. Well, a box has lots of sides on it. It's got two of the little end caps. It's got two of the sides. It's got a bottom. And it's got a top. So there's two of those. So there's 1, 2, 3, 4, 5, 6 pieces that make up surface area. So while volume is a nice length times width times height, surface area can be a little bit more involved. Surface area, you've got 2 length times widths, that's the 2 bases, plus 2, I'm going to leave the 2 factored out, 2 of the end caps. The end caps are height times width, so height times width, plus 2 of the sides, and the sides are length times height, so length times height. So that's surface area. It's similar to perimeter, except you've got an extra level of sides. And there's more multiplication going on, clearly. Oops, keep banging that, sorry. Okay. So, and let's see, we're also told that the length is equal to twice the width. So the problem is we have lots of variables and lots of equations going on here. So we'd like to put this together, minimize the variables we have. The nice thing is we know this volume as a value. We know that volume is equal to 216 because they tell us it's equal to 216. We know this surface area is equal to 252. So as I said, I'd like to eliminate us down to as few variables as possible. Since we know that the length is equal to 2w, we could take out all these L's, or both of these L's, and put in 2w's, and this one. And then we could really solve this either for height or for width. I'm going to choose height. So if we solve that volume equation for height, we'd have height equals the 216 over length times width. I'm just dividing the length and width off from the 216. That's our height. Furthermore, that since the length is equal to 2w's, where this length is, we can replace it with a 2w. So we even have 216 over 2w times w, so 2w squared. Oh boy, I hope you can see that. Let me not use peach. So let me actually move this down a bit and just redo that. So we know our volume, our length times width times height, is equal to 216. Since we want to try to eliminate some variables, and we have a lot of things in terms of w, let's go ahead and solve this for h, so that way we can get rid of the h's in here. So divide both sides by L and W, 216 over L times W. But since we also know L is equal to 2W, I'm going to let that L equal 2W, and we get 216 over 2W times W. So this L became 2W. And that's going to give us a height equal to 216 over 2W squared. Pull those fractions down and get 108 over W squared. So wherever we see an H, we can replace it with that. Wherever we see an L, that L can be replaced with 2W. So we go back to this big formula for surface area, and we start with length times width, but that length can be 2W times width, plus the height, that's 108 over W squared times W, plus our length, 2W times H, and H is our 108 over W squared. And that's all supposed to equal 252. Now notice this thing was all times 2, and I hope you don't mind if I just divide that 2 out before I do any of that work. It'll save me some trouble later. So that gets us down to an equation in only widths. So for the box in question to have this volume, the 216, to have the surface area of 252, and to have the lengths equal to twice the widths, that only happens when this equation is true. So all we need to do is find solutions to this equation. Hopefully that goes well. So a little bit of simplifying here. How about the 2W times W, nice 2W squared. A little canceling those W's out, so we get 108 over a single W. 2 times the 108 is back to 216, but that W is going to cancel with one of those W's, so we have another W on the bottom. And I hope it's okay to take that straight to, what was that, 126. Okay, add those together. 2W squared plus, what is that, 324 over W equals 126. Now, that's not the most lovely equation that we've ever worked with here, so it might be nice to manipulate that a little bit, make it a little more pleasant. So let me again make myself some space here. So we've got, I'm just going to recopy this. It's always a good habit, by the way, when you're working on something sizable, when you go to the top of the next page, don't try to do work. Just try to recopy it, check and make sure it's copied properly, and then progress. It'll save you those copy errors as you go from one page to the other. So, I don't like this W in the denominator. We're not afraid of fractions, but when we can avoid them, it's nice. So, to get that W out of the denominator, I'm going to multiply both sides by W here. 2W to the third plus 324W equals 126W. Oh, and that was over W, sorry. And those W's cancel. So 2W to the third, I'm going to subtract that 126W over, plus just a clean 324 equals 0. Now we've got a polynomial set equal to 0. It would be nice if this polynomial was a quadratic, but this is W to the third, so it's not a quadratic. So we're going to have to use our bigger tools like our rational root theorem and our synthetic division and all those toys. But it's nice to notice that each of these are a multiple of 2. So it might be nice to divide that 2 out before we get too far, just to help avoid using numbers quite as big. Was it 216? No. How about 162? My brain's not working. So, yeah, 162. Yeah, 150 plus 12. Okay, yeah, 162. So, that's what we're trying to factor. Now, again, if it was a quadratic, we could ask what multiplies to this and adds to this, but it's not a quadratic, so we're stuck. But we know the rational root theorem. And it has a lead coefficient of 1, so if it has a rational root, that rational root has to be a factor of 162. And 162 is actually kind of a nice number. Oops, jumped the gun there. 162 is 2 times 81, and 81 is 3 to the 4th. So this 162 is 2 times 3 to the 4th. That means anything that's going to be divisible into that 162 and be nice and rational is going to have maybe a 2, but a whole bunch of 3's. So things like 3, 6, 9, 12 can't be in there. You need another 2. 27. So I would tend to start by looking at multiples of 3. So you might check 2, 3, 6, 9, and of course positive or negative. Maybe 18, 27, things like that. But of course, because our length times width times height has to be 216, our numbers can't get too terribly big. So I'm going to stick with, check things like 2, 3, 6, and 9. And I don't even, and of course it could be a 1. Right? It can always be a 1. Now you could look at the graph to give yourself a better sense of checking. I'm going to start checking with the 3s, 6s, and 9s just because I've looked at the graph. So let's start with that 3. So we're going to do synthetic division with our 3. Our coefficients are 1, 0, negative 63, and 162. Now, do again be careful about that 0. That 0 is for the 0w squared that's in there. Forgetting those zeros will always cause you trouble. And you can see why I like this 3. At some point, we're going to be multiplying 3 by this fairly large number, trying to get up to this fairly large number. A 1 would never do that. A 2 might do it, but I don't think so. So I think I like that 3. But, worst case scenario, you check a couple things that you don't need to. You practice your synthetic division. Everybody's happy. So the 1 comes down. 1 times 3 is 3. Add them together, you get 3. 3 times 3 is 9. So 9 minus that is what? Negative 54. And negative 54 times 3 is indeed negative 162. Just like we wanted to have happen. And that leaves us right away with a quadratic, x squared plus 3x minus 54. if we want to know where that is equal to 0, this one's even factorable. Because that's what, 9 times 6 gives you negative 54. It's got to be a positive 9, then negative 6 to give you the positive 3. So we get x equals 6 and x equals negative 9. So our solution to this equation is, well, these should be w's, I suppose. Those should always all be w's. But the solution for this is the width to be either 3 or 6 or negative 9. Now, since we are making a real box here, that negative 9 doesn't make sense in context. So really, we're just left with our 3 and our negative 9. Or sorry, our 3 and our 6. If we wanted to look at what this graph looked like, we've got an intercept at 3, an intercept at 6, an intercept at negative 9. It's a third degree upward facing polynomial, so this thing is going to go like that. So, we got our nice 2 solutions at 3 and 6. So if we wanted to check and see what values we're going to get at 3 and 6, we can go back to our kind of control equations here. So if the width is 3, the length has to be 2 times 3. 2 times 3 is 6. And the length times the width times the height, 3 times 6 times h, has to be 216. So 18 times h has to be 216. And we just have to figure out, what do you multiply by 18 to get 216? What do you multiply by 18 to get 216? I don't know. When in doubt, divide. 18 goes into 21 once, 18. That leaves 36, 2. So how about 12? So the height would be 12. So that's one set of dimensions. If the w is equal to 6, then the length would be twice that, 12. And we already know that 3 times 6 times 12 gives us 216. So our height would then have to be the 3. It's really the same box, just a different orientation. This one's tall and skinny, that one's short and long, but just same orientation or same box gives us the same volume. So this is actually a nice practical application of a lot of the tools that we've been talking about. We're going through setting up a very nice, normal, everyday little box area volume-y problem, and all of a sudden, while working with that, a third-degree polynomial pops out. And as I said on some of the other videos, when the third-degree polynomial pops out, these tools have to come to mind. I've got a third-degree polynomial I need to solve. It won't factor normally. So rational root theorem. And rational root theorem will start breaking it down. I mean, this one breaks down really nicely, but it doesn't have to break down nicely. So hopefully you like this example. Again, there are going to be problems like your fence problems, like these box problems on pretty much all of your tests. And as I think I said before, for many of you, you're not going to be dealing with boxes and areas and volumes and lengths. But anytime you're looking at restricted resources, the hours working versus payroll staff and the relationship between your different staffing or your different cost options. Anytime you're looking at interrelation between restricted resources, these types of box problems are metaphors for just about any type of restricted resource relationship. So if you're going into human resources, if you're going into money management, resource management, if you're going into any application where you won't have an infinite amount of everything you want, this type of stuff can come up. So keep that in mind when you're doing these problems. It's really a metaphor for a larger type of problem. Okay, I'm going to post that. And if you have any questions, let me know.